Welcome everyone. In this session, we are going to discuss about the topic supervised network learning paradigms under the subject neural networks and its applications. So today we are going to discuss about the perceptron convergence algorithms. So the perceptron convergence algorithm is a related to a learning process of a perceptron. That is a simple model used in the machine learning and the artificial neural networks for binary classification. So, what is the concept behind the perceptron convergence algorithm? So, the perceptron convergence theorem states that if the training data is linearly separable, the perceptron learning algorithms will converge to a solution in a finite number of steps. So, this means the algorithm will eventually find weight that correctly classifies all the training samples. Then we'll see what are the steps included under the perceptron convergence theorem. So these are the different variables and parameters which is used in the perceptron convergence algorithm. X of n represents the input vectors, W of n represents the weight vectors, B of n represents the bias, Y represents the actual response, D of n represents the desired response, and this is given as the learning rate parameters. So the first step is the initialization. First, we need to initialize the weight and the bias values. So basically, we'll be setting the weight values often as zeros. Then perform the following computations for different time steps 1, 2 up to n. So after initialization of the weight and bias, we'll be going for the activation. That is at a time step learning, particular learning rate. So activate the perceptron by applying continuous valued input vectors x of n and the desired response d of n. So after initialization, we'll be activate the particular neurons by applying the suitable input vectors and obtaining the desired response. So after the activation of the neurons, the computation of the actual response can be performed by using these formulas. So y of n is the actual response, so which is given by the sign function of w power t of n into x of n, where the actual response will mainly depends on the weight and the input vectors. So after computation of the actual response, we'll be going for the adaptation of weight vectors. So we will be updating the weight vectors of the perceptron by using this formulas. So W of n plus 1 is equal to Wn plus learning rate parameter of d of n minus y of n into x of n. So this W of n represents the weight vectors. So this is the learning rate parameters, and D of n represents the desired response minus Y of n is the actual response, so which will be multiplied by the input vector x of n. So this is the assumption can be made. That is, if the particular input x of n belongs to a class, particular class 1, then the desired response output is given as plus 1. Or in case if the input vector belongs to the class 2, then the desired response value can be made as minus 1. So finally, we'll be obtaining the plus 1 or minus 1 as the desired response. And this process will continues. That is the increment time step by 1 and go back to the step 2. So the same process will continues until no classification errors will occurs. So this is the brief summary of the perceptron convergence algorithms. That is the first one is the initialization. So the initialization can be performed by the weight and the bias values. So basically, so that can be set as a zero value. So after initialization, the activation function of the neurons can be made. So after the particular neurons got activated, we need to compute the actual response by using this formula. So after computation of the actual response, we'll be going for the adaptation of the weight vectors. Then the same process will continuous until there will be no errors. So when does the convergence will occur? So the algorithm converges when the data set is a linearly separable or a hyperplane exists, so that separates the classes. So under these two conditions, the algorithms can converge. So examples, the problem like AND or OR gates can converge. So these steps only we look. before. So that is a d of n is equal to plus 1 if x of n belongs to particular class, or it can be minus 1 if x of n belongs to the class 2. Then for the adaptation of the weight vectors, we'll be using this particular formulas, where this eta is the learning rate parameters and the difference d of n, that is a desired response minus y of n, plays the role of an error signals. So until the magnitude of the errors becomes a zero, so this process will continuous. So this will simply mention how fast the particular network will converge. So the next one is the delta rule. So the delta rule is also called as Woodruff learning rule. It is a fundamental learning rule used in the neural networks for weight adjustment based on the error between the predicted and actual output. So it is commonly used in the single layer perceptron, and it is a special case of gradient descent applied to the mean square error loss function. And these are the different steps we are using for the delta rule derivation. We can use the delta rule specifically for the weight adjustment, so that we can able to reduce the magnitude of the errors. So the step one is that define the perceptron model. So we need to define the perceptron model. For example, consider a single layer perceptron with the following elements. Input x1 up to x of n represents the input, and w1 up to w of n represents the weight, and W naught represents the bias value. So this will be often included as an extra weight. Then the net activation function will be given by this formulas. That is the multiplication of the input weight into the multiplication of the input along with its weight. Then the summation operation will perform with this multiplication, plus finally W naught will be added. Then the output activation function can be given as the function of the net. So this is the first step. We need to define the perceptron model. So the step two will be define the error function. So the error function for a training sample is given by the mean square error. So we can apply this formula for that 1 by 2 of t minus y whole square. So this particular factor 1 by 2 is included for simplifying the differentiation. So the step 3 will be compute the weight update using the gradient descent. So the gradient descent is used in the backpropagation technique to minimize the errors by updating the weight. So the weight update rule can be used. So new weight is equal to old weight plus the changes in the weight. So in this particular formula, the theta represents the learning rate, and the dou E by dou of Wi represents the gradient of the error function with respect to Wi. So this particular gradient of error function is used to update the weights. So thereby we can able to minimize the errors in the networks. So which will make the desired output and the actual output to be equal values. So step 4 is finally compute the gradient. So to compute the gradients, we'll be using this particular formulas. And step 5 is the derive the delta rule. So by substituting the back in this part, the last equation, so we'll be obtaining the values, the changes in the weight value is equal to learning rate parameter of t minus y into x of I. So this is nothing but the delta rule. So which updates the weights based on the difference between the target and the predicted values. So the interpretation based on the final result is the error term t minus y determines how fast the weight should be adjusted, and this learning rate parameter will controls the how fast the model will learn, and the activation function derivatives ensures that updates adapt to the new nonlinear activation function, example sigmoid or tan h. These are the various variations and the extensions to the back propagation. Stochastic versus mini batch gradient descent. Batch gradient descent will updates the weight after computing gradient for the entire data set, So SGD represents stochastic gradient descent. So it will updates the weight after each training sample, increases noise, but improving the convergence speed. So the mini batch gradient descent, so it is a compromise where gradients are computed over small batches, improving the stability and the performance. And next one is the momentum based back propagation. So it introduces a momentum terms to smooth out the updates, which will reduce the oscillations and speed up the convergence. So these are various adaptive learning rate parameters. ADA-grad, RMS prop, ADAM, resilient back propagation can be used. And this is a various extension to the back propagation. So extension includes the second order methods. So it will use the Hessian matrices to adjust the learning rates, improving the convergence. So next one is the regularization techniques. L1 and L2 regularization can be used, which will prevent the overfitting by penalizing the large weights, back propagation through time, and parallel and the distributed back propagation. So these are the various extensions to the back propagations. Thank you all.